Hello, how are you doing? This is Mike here, and in this video we're going to talk about the graphs of our hyperbolic functions and maybe get into a little application of hyperbolic functions and where we see them. So I think that's important for us in order to really understand hyperbolic. So I like to go ahead and graph these, and I'll just do maybe two. I'll do two at a time. Well, I'll do one at a time, but I'll do two adjacent to each other, and then we can see the relationships of them. So the first one I'll do over here is I will do f of, let's go ahead and do f of x. Let's do our cosh. I think it's a little bit easier to do cosh, our hyperbolic cosine. And then, I don't know why I see that one better. And then over here in blue, well, actually we'll do it in blue. And we'll do f of x is equal to sinh, hyperbolic sine, So the nice thing about cosh is basically it's almost a parabola. It's almost a parabola, and it shifts up at one. It looks something like this. But it's slightly different. It actually has some asymptotes, but these are probably different asymptotes than you've ever heard before. And the asymptotes that cosh has is something called curvilinear asymptotes. So these are curvilinear. So I'm going to do these in yellow so we can see them. So these are curvilinear asymptotes. So curvilinear oops, didn't do that right. There we go. So here this is one curvilinear asymptote, and then here this is another curvilinear asymptote. So this curvilinear asymptote, the one that is decreasing, is going to be 1/2 e to the negative x. And you can remember that because he's decreasing. This point actually right here is going to be at 0, 1/2. So this asymptote, this curvilinear, I'll write that out for you, curvilinear asymptote. This curvilinear asymptote is going to be, I'm sorry, the curve of cosh will be asymptotic to 1/2 e to the negative x, 1/2 e to the negative x as you approach negative infinity. So here's negative infinity over here, here's positive infinity. So if we were to ask what is the limit as x approaches negative infinity for cosh of x, and this should be, this should be cosh of x. So I left off my variables, that's not good. So what is the limit as x approaches negative infinity of cosh of x? So as we approach here, right, we're really approximating the limit as x approaches negative infinity of 1/2 e to the negative x. And we see here that as we approach negative infinity, that this graph is going to go off to positive infinity. So I think that will even help you as you approach, as you look at some of the limits. So that might help a little bit as well. This curve over here is going to be 1/2 e to the positive x. So that's going to be the curve that is increasing. So it's increasing. So maybe I can show it here. Hopefully you can see my little green marker. Maybe I'll just highlight. So that will be, well, that's very bright. So that'll be 1/2 e to the x. So as we approach positive infinity, so let's say, look at the limit here. The limit as x approaches positive infinity of cosh of h. This will be equal to, or approximately equal to, the limit as x approaches positive infinity of 1/2 e to the positive x. And we realize that 1/2 e to the positive x, we are also approaching positive infinity. So just keep that in mind. I think that's a really neat way to look at this, is looking at these curvilinear asymptotes. If we want to identify the domain, so there's a domain. So let me write out domain so we don't get confused. A domain and then a range. So the domain, hopefully we can all look at this graph and recognize the domain will be all real numbers. However, the range is going to be interesting. The range will start at 1 and go all the way to positive infinity. So that's going to be how we identify cosh. Sinh is a little bit different, but it still has those same curvilinear asymptotes. So I'm just going to go ahead and graph these curvilinear asymptotes. Well, it actually doesn't have the same ones. It has similar ones. So this is going to be the first one. This is going to be the 1/2 So this is going to be 1/2 e to the positive x. And the other curvilinear asymptote that will exist will be negative 1/2 e to the positive x. Sorry, negative 1/2 e to the negative x. Sorry, there we go. So it's going to be, that was a little bit of a mouthful. So it's going to look something like this. So this curve is negative 1/2 e to the negative x. It's flipped across the x-axis and flipped across the y-axis. And our sinh will start down here. It's asymptotic. It's asymptotic. And remember earlier we said sinh of 0 is equal to 0. So here we will continue. I lost my cursor. There we are. So we're going to continue, and we will be asymptotic to 1/2 e to the x power. So we do have those two asymptotes. And they will help guide us in drawing our paths. So this is slightly different because we recognize the domain here. The domain here is going to be negative infinity to positive infinity. And the range will also be negative infinity to positive infinity. So hopefully you can look at this and recognize the limit as x approaches infinity of sine of h will approach infinity. So I could actually write that out so we can see it. Maybe we could just do that. I just don't want to run out of time on this video. The limit as x approaches infinity of sinh of x. As we approach infinity, our curve goes to infinity. However, as we approach negative infinity, our curve will then go to negative infinity. So it goes down to negative infinity. Oh, I just lost my curves. Great. So did not like that at all. So I'm just doing that quickly. That makes me so irritated. So hopefully you got that. If you need to, just reverse back into your into the video. So now let's go ahead and try drawing tangent and cotangent, hyperbolic cotangent. So these ones are a little different, a little bit different, but a little bit fun too. So so let's go ahead and track. I'm going to do it in red again. So let's say y equals to hyperbolic cotangent of x, and in blue we'll do y equals to hyperbolic tangent of x. So we have cotangent of x, and then we have tangent, hyperbolic tangent of x. So cotangent of x, I like doing this order just because, I don't know, this makes sense to me, but you can do it however order you want. Cotangent of x is going to have some asymptotes as well. So up here at 1 and negative 1, we're going to have some horizontal asymptotes. We're going to have some horizontal asymptotes. So cotangent, hyperbolic cotangent will look something like this. So it's asymptotic here. And then it will also be asymptotic down here. And there is a vertical asymptote that exists along the y-axis, which is x equals 0. So hyperbolic, I did the wrong way. I did them in the wrong color. Look at that, I did it backwards. So it looks something like this. And it looks like that. So hyperbolic tangent also has some asymptotes, and these asymptotes exist at positive and negative 1, just like we saw before. So positive 1, negative 1. So we have some asymptotes that exist as well. And with hyperbolic tangent, remember we said hyperbolic tangent of 0 is also to 0. So this is going to look something like this. So it looks like this. I think that's relatively easy. Let's go ahead and hit our domains and ranges. So the domain of hyperbolic cotangent, hopefully we can see here, it starts at negative infinity, goes until 0. 0 is not included. Then we go back at 0 and go to positive infinity. Our range will start at negative infinity, go until 1. 1 is not included. I'm sorry, negative 1. Then we start again at positive 1 and go to positive infinity. So the domain of hyperbolic tangent, is going to be all real numbers. So we love working with hyperbolic tangent. And then our range is going to start at -1 and go to +1. So these are asymptotic, so they're never actually going to touch and won't actually ever get there, so we're not going to include any of those values. And, oh, I hope I did that. Let me just check for, okay, good, yeah. So the one that we do include is going to be our cosh. So let's go ahead now and graph the last two hyperbolic functions. Let's go ahead and graph our last two hyperbolic functions. And this is hyperbolic secant and hyperbolic cosecant. So I just have the worst problem saying sec and cosec. So it doesn't work for me as well. So let's go ahead and look at this guy. This is going to be y equals to sec of x, and then in blue we'll do y equals to hyperbolic cosecant of x. So sec does have a horizontal asymptote which exists along the x-axis. So it actually looks like a bridge, and that's where you actually see this hyperbolic function occur in engineering, is because it actually looks like a bridge. And it never touches the x-axis, which is slightly different than what we'd see in the application, because we know a bridge ultimately does touch ground again, but it does visualize like a bridge. And then cosecant, hyperbolic cosecant, is going to have a vertical asymptote along the y-axis and a horizontal asymptote along the x-axis. So it never actually touches, never actually touches at these points. There we go. Where's my little, there we go. So let's go ahead and hit the domain and range of sec, hyperbolic secant, and then hyperbolic cosecant. So the domain here, we see this is really nice, starts at -infinity and goes to +infinity. I should have indicated this point here is going to be 0, 1. And then our range will start at 0 but not include, and it will actually touch up to 1. So be careful, because it does not include 0. It is tangential. I'm sorry, it is asymptotic, but it never touches. So hyperbolic cosecant, the range, let's start with the domain of this guy. The domain will start at -infinity, go to 0, not include. Start at 0, go to +infinity. And the range actually looks very similar, which is one of the reasons why I like it. So I love that symmetry. So now, when you actually can see the graphs, I think it's a little bit easier to reflect upon which one of these functions is even and which one of these functions is odd. Remember, even functions have symmetry with respect to the y-axis. Odd functions have symmetry with respect to the origin. So if we look at this guy, let's start to look at, of course it's gone. So of course it's gone. So let me go ahead and draw this relationship here. So it looks like this. So notice here, cosh has symmetry with respect to the y-axis, and since it's symmetric with respect to the y-axis, it's also going to be an even function. Notice here, sinh has symmetry with respect to the origin. If you rotate it 360 degrees and you put your pen right at the origin, you're going to get the exact same function. So looking at it graphically, we can see that this is a very nice odd function. If we see cotangent of the hyperbolic cotangent, we see that this also has, if we were to put our pen right here and rotate it 360 degrees, we're gonna have, I'm sorry, 180 degrees. I think I said 360 up here. If we rotate this 180 degrees, this 180 degrees, then we also have origin with respect to the, symmetry with respect to the origin. So this is also going to be an odd function. This, if we rotate tangent, hyperbolic tangent, we are also going to have symmetry with respect to the origin, so this is also an odd function. Notice that the hyperbolic secant has symmetry with respect to the y-axis, so this is actually an even function. And that would make sense because secant is just the inverse of cosecant. So that would actually make sense to me, because there's a formal calculation to determine even and odd functions, but we can just look at the graphs and recognize it. Then hyperbolic cosecant has symmetry with respect to the origin, so this is actually going to be an odd function as well. If you want to test these theories for even and odd functions, remember, even functions have a unique relationship that f of negative x equals to the original function, and odd functions is f of negative x equals to the negation of your original function. So, for example, if we were to plug in cosh of negative x, everywhere we see an x in cosh, we would have to plug in a negative value. So this would give us e to the negative x. This would be e to the negative x, and you go back and you reflect on whether or not cosh has a positive or negative, but hopefully remember this is going to be a positive, but this positive does not change because the only variable that changes is going to be the variable of the exponent. Remember, our original cosh function was e to the x plus e to the negative x, and this was all divided by a value of 2. And this is still divided by a value of 2. So notice here I plugged in the negative. Here I plugged in, let me just show the two negatives. So this was a negative and this is a negative there. So this will actually give you e to the negative x plus e to the positive x still all over 2. And this is exactly the same thing. We just have to flip-flop these. And we'll have e to the x plus e to the negative x all over 2. So you can prove an even and odd functionality using your hyperbolic functions just by plugging in either negative x and getting your original function, or plugging in negative x and getting your negation of your original function. But each one of your hyperbolic functions is either even or odd. I remember that the cosh is the positive, he's the even. I say positive because I see this positive value right here. He is even function, and the inverse of cosh is going to be sec, or hyperbolic secant, and that's also the other even function. All the rest of them are odd.